In this presentation, we'll look at different guidelines for borehole heat exchanger design and construction, mainly aimed at regulators and policymakers. But of course, if we're talking about protocols, we also write protocols for the designers, the installers, and the drillers. Now, first of all, we want to use the ground as a source of energy because it's a very energy efficient system, and we can use the ground for thermal storage. Moreover, they have a very long lifespan, somewhere between 30 and 50 years at least. And this means that, we have a long lifespan and a high efficiency, which means that we can save a large amount of CO2 emissions, but also save a large amount of primary energy use for climatization of buildings. At the same time, the ground is a sensitive environment, so we want to have some protection of ground and groundwater resources. And this means that we are keen to ensure the quality of design, construction, and operation. So in this presentation, we'll look at some key aspects of regulation guidelines. We look then in more detail at the European norm for closed-loop systems, and at a certain moment we can go into, in different presentations, some examples of national regulations and certification. Now, advantages of closed-loop systems, of borehole heat exchanger systems, are that they can be installed in virtually any geology, that they're scalable from a single family house to very large collective systems, and can easily be integrated with phase developments of larger areas. It is a robust system. Once installed and properly tested, there is virtually no maintenance of the underground infrastructure, and at the same time, it has a very long lifespan, up to 50 years or something like that. Now, key aspects of regulations when we think about what we want to regulate, what we want to check for closed-loop systems. First of all, of course, protection of the geological and soil resources, groundwater quality, and things like that. The main aspects here are that we want to prevent mixing of different groundwater qualities. In the little picture on the right, you can see a geological profile with a lightly colored gray area between a pink and a darker green area. And this is a clay layer between two different water-bearing formations. We want to prevent boreholes drilling through this clay layer and perhaps having the risk of mixing of groundwater. The mitigation here is to have a correct sealing of the borehole, usually through backfilling with clays and grouting of the borehole. Another risk is the emission of pollutants like antifreeze due to leakage in the system. Usually this leakage occurs in the horizontal part. Moreover, if you have the correct quality of antifreeze, it breaks down both biologically and in aerobic and anaerobic circumstances. So actually the effect of some leakages is very small, and very little leakage occurs if you have a good quality of system. So the mitigation here again is the quality of the materials and workmanship, and also the fact that pure glycols like monopropylene glycol or ethylene glycol, or even alcohols like they're used in the north of Europe, biodegrade very rapidly in the ground. Another aspect is to have compliance with operational limits. For instance, we want to have a maximum, minimum temperature, a maximum injection temperature and a minimum injection temperature. For instance, an injection temperature not below -3 degrees, because we want to prevent freezing of the soil and freezing of the borehole heat exchanger. Another aspect can be energy balance. In the Netherlands, for instance, we want to prevent the ground from heating up, so we allow a net heat extraction of the ground, but we do not allow a net heat injection of energy into the ground. Other key aspects are, for instance, to ensure the quality of design, because the quality of design, of course, then also ensures the efficiency for the end user. Again, for the construction, the quality of materials, the ground heat exchanger, the vertical part, the horizontal part, the connections, and workmanship are very important. And at the end of the day, we also want to know where the systems are installed. So documentation of the design and construction is very important. Prevention of thermal interference, which we deal with in another presentation, is of course important, and possibilities for planning of ground source energy systems, where not every installer decides exactly for himself how he wants to dimension the system and construct the system, but where there is an overall planning for a whole area where different installers can then realize the systems. Support for installation and planning. Here, an example of the Dutch WKO, the website where we have a documentation of all the systems installed, and you can get some information about both closed loop and open loop systems installed, and also see whether you are in a groundwater protection area and such. A public database with several key performance indicators of the installed systems, like the borehole coordinates, depth and total length, design energy, heating, domestic hot water, cooling demand, at least on a yearly basis, and also the design efficiency for heating, domestic hot water and cooling, the installed thermal capacity, and then there is coupled to this a procedure to assess potential thermal interference. And of course, at the end of the day, municipalities or other authorities can have a method to plan for ground source heat exchange, ground source systems, and develop so-called ground source energy plans. In a number of cases, monitoring and reporting may be required. In the Netherlands, for instance, we have a monitoring obligation for all systems with the exception of single-family households. And this will provide insight in the actual energy use and efficiency, which you can feed back into the design loop. And it is also used to enforce regulations with regard to energy balance, minimum and maximum temperature. Monitoring, of course, can also be important for preventive maintenance because it will tell you how the system is operating and gives you the possibility to check before you go to site, and maybe you know already that a temperature sensor needs to be replaced. However, on the other hand, monitoring does require a bit more expensive equipment, so it increases the total cost of the system, and for smaller systems this can be a significant burden.